Sometimes people like to know something, not every day, only sometimes. Oh. Come on, machine. Machine. Oh, finally. Who's coming? Maybe drink one more scope. More scope. of everything. Time to switch. Time to switch. Yeah, something going on here. Yellow line, blue line, another yellow line. 1, 2, 3 scopes, 2 generators, a lot of everything. And what's this all for? This all to show one of the old signal processing tricks. Sometimes extremely popular. Nowadays also used. Can we without? First switch closer. Yeah. Here is my demo object. And the center of my object is this. Yeah, this one. One electron valve. You stop. It's a special type of electronic valves. We spoke a bit about valves, yeah? Let's say this was DC. We have N plus another current, and I showed depends on a God, yeah? And how I used this triode? As a linear amplifier, yeah? Was something like this. Or you can't remember. When I spoke on system with return. Huh? You know what we usually do with mobile devices on premise? What's a better idea? Nail them to the wall and write area of information security. How can I represent my triode? As a resistance controlled by a God. A God is unknown. And I use this linear part of characteristic to perform a voltage amplification, to act as a linear amplifier. Yeah? It was? This one has a much interesting design. My previous was triode, 3 electrode. Cathode for ground, anode for high potential, and GA for grill, 1 control. Here, 1, 2, 3, 4, 5, 6, and 7. This one has 7 electrodes. Grounded, grounded, grounded. Here was 250. Here I have a 2, 1. You see what this comes to? It's also a variable resistance, but it has 2 control inputs. I can use it to mix 2 signals. I can add 1 signal, or I can put 1 signal here. I can put 2nd signal here. And why all this intermediate grid? To isolate them. They all schematics will be independent. Why it's so important? It's important. I can tell you, it's from the history. During the war, Allies started to detect German submarines with radar. Germans invented radar detecting receiver, but this receiver had one flaw in its design. No insulation between circuits. So, Allies start to seek German submarines by emission of this radar detector, without putting themselves on a danger by radar emission. So this insulation is important. It's electronic insulation to prevent crosstalk between circuits. So this nice valve allows to control flow by 2 signals, like amplifier with 2 independent inputs. And here I have 2 signals. One from my signal generator, emulating an amplitude modulated signal. I change the scale. Okay, come on. One megahertz modulated with 1 kilohertz. Okay. And what about second one? Second one shown here. It's from local source called heterodyne. Here I have a second valve, 6SO8. Idea, I have 1 signal, it's in my case amplitude modulated, but it's not important. This signal is 1 at 1 megahertz. Second signal is from local source of variable frequency, heterodyne. I can change its frequency here. Here you can see the signal, and it's now 1.6 megahertz. If I put via this double input amplifier, if I get a sum of that, what I will get as output? What's the product of sum of cosines? Can someone tell me? Sum of cosines. Cosine A plus cosine B. No response. Silence. Okay, let's think what we have. This is one and local heterodyne. Okay, this is signal and this is heterodyne. With frequency omega signal and omega heterodyne. So this will be cosine omega s and this heterodyne cosine omega heterodyne time. Can I do this? I can, let's start with very simple. Only carrier and only heterodyne. I can draw a very simple vectorial diagram. This is vector with amplitude, let's say signal, and rotating with the frequency omega signal. Plus this one rotates as omega heterodyne. What will be the sum? This one has a magnitude of heterodyne. What will be sum? Theorem of cosine, school trigonometry.
It will be 2 cos
2
cosine the square goes to minus.
Wait 1 second. Let's mark this angle. What should I write?
The square goes to the minus.
Yeah, I need to write square root from heterodyne square plus omega signal square, yeah? Minus 2 max heterodyne omega signal multiplied by cosine of this theta, yeah? But what's the theta? It's inside. Angle theta is omega heterodyne minus omega signal multiplied by time, yeah? Difference of frequencies in time. If we assume what this one stands, this one will rotate relatively the signal what we saw when? When we saw this such signal? Telemann's experiment. Yeah? Remember? Singing ball. What I'm talking about? We have the same sum of signal as with the Telemann's experiment. So we will get something like this. And this one cosine moment. I didn't show. The amplitude of this yellow vector changes in a law of cosine. But angle of it also changes. Angle of it I can draw like this. One position this one, second position like this. It will change not only amplitude but also its angle. Amplitude, if they are equal, changes from 0 to double. And angle, in this case, will change in what? From 0 to 45 degrees in both directions. Yeah. So if I can mark, let's say, C, this vector, this angle. We are working on something complex. Where amplitude changes from double S max, and we can also write sine of this angle and its maximum value will be O max signal divided by O max heterodyne. We can say what resulting frequency can be defined as omega heterodyne plus we can get its wobbling. This wobbling has its own frequency in stable regime, and we can take this frequency as a derivative of the angle shift. Yeah? Our angle theta, actually, if we take a look deeper, is P minus delta omega time. So, cosine of it will be minus cosine of, delta omega time. Yeah. So, we can write this resulting voltage, this yellow voltage, as heterodyne voltage square root 1 plus U signal max square divided by U max heterodyne square plus square root continuous plus this part is double U signal max divided by U heterodyne max cosine of delta omega t. Yeah. This is this yellow voltage. This formula gives us law of this, how to say it, this borderline. I can rewrite it in a bit, it looks a bit strange. It looks a bit strange, but it has its max plus U signal max can be written like this: 1 plus U signal max square U heterodyne max square plus double cosine delta omega t multiplied by US H divided by 1 plus US square U heterodyne max square plus double U signal max divided by U heterodyne max. This is max. Yeah. Here we can see one tricky thing. The closer if signal max divided by max of U heterodyne is much smaller than 1, result will be sine, because double result will be very similar to sine of delta omega. But if they are close, we will get something more complex. And if we have 1, in case the voltages are equal, we will get something like this field with high frequency. Here the U signal max divided by U heterodyne max is 1. take a look on a case where Umax signal is much less than Umax heterodyne. In this case, we will see what? Large U heterodyne and very small U signal. Meaning what resulting vector will have a very small change in angle. It shifts, it changes in amplitude, but has a very small angular shift. That's means what I can approximately write this voltage, this yellow voltage, as approximately U heterodyne square root 1 plus double U signal max U heterodyne max cosinus delta omega t, again approximately equals to U heterodyne 1 plus U heterodyne max cosine delta omega t. What is, did we saw something like this? Hour before, it's an amplitude modulated signal. Mark this as a modulation index. And you will see what? Amplitude modulated signal with the delta omega. What do we know about amplitude modulated signals? Amplitude modulated signals will have omega signal plus omega heterodyne, omega signal minus omega heterodyne. Yeah? Sidebands. You missed it. And you missed amplitude modulated signals. Those who here saw amplitude modulated signals and saw the spectral diagram, what we have? USB and LSB. And central useless band. Here is a case when signal is very small. For a large signal, we will see the different picture. In case Umax signal equals to Umax heterodyne, we will have a triangle like this. Here is our Xi, here is our theta. Here, resulting rotation frequency of this vector, very simple. This omega will be omega heterodyne plus delta omega by half. Meaning omega signal plus omega heterodyne by half. And amplitude of the sideline will be heterodyne max square root 2 1 plus cosine delta omega t, or double heterodyne max cosine delta omega by half. And what all this mean? So, signal of sum should contain in any case one component. And this component is in frequency delta omega. In both cases, I took border case. We will see component delta omega. Now, let's take a look. This is S with frequency omega S. This is heterodyne S max heterodyne cosine omega heterodyne time plus n. What's the symbol for? Band pass filter. What frequency should I write? Idea. In each case we had one component, delta omega. Omega minus omega heterodyne. Yeah? In my example, omega signal, yellow line, is 1 megahertz. Maybe I will. Now signal is unmodulated. 1 megahertz. Omega of the heterodyne 1.45 megahertz. And here I have a filter with bandpass frequency. It should be 465 kilohertz. It's a bit different because here is a peak 443. Actually, it's a bit damaged. You see what happens? No? One megahertz, 1.4 result at a different frequency. Now, okay, what's the different frequency? What do you see at yellow line? It's a 1 megahertz amplitude modulated with this signal. 1 second, I'll switch. Maybe someone. my original signal. I have first rectangular signal, 1 millisecond. It can be represented as this diagram. 1 kilohertz, 3 kilohertz, 5 kilohertz, 1, 1/3, 1/5. I use it to amplitude. Should be something like this. Inner field is 1 megahertz. Amplitude, 1 megahertz, approximately 300 meters, it's the middle of AM radio broadcasting range. What will be spectral of this signal? You missed everything. For this signal, spectral diagram looks like frequency, 1 megahertz carrier, one megahertz plus 1 kilohertz plus 3 kilohertz plus 5 kilohertz minus 1 minus 3 minus 5. That is a spectral diagram of amplitude modulated signal. Now this comes to the mixer with heterodyne signal 1.44. This one will be summed with signal 1 spectral line 1.443 kilohertz. This means comb not needed. What will we get? Blue line. One moment, I will try to catch blue line. Source, channel 2. Oh, 1 second. I will show spectral diagram. No, I will not be able to sort. This will not work. Okay, channel 2 here. Here is the result. And what's the frequency of result? Four 3 kilohertz. Wait one moment. Can I get frequency? Can I get 1 second? I'll do one trick. I will switch this I will it's unlucky. Maybe I will cut. Sorry. Channel 2, I will freeze it. Here is our signal after. And I need its spectrum. Here is spectrum of my use what I have a resonant load here. I got a resonant load. I unplug this. What will I get? One moment. Scale, scale, scale. Yeah. It's a small second one. But in this case, when use I don't get second. I need to get I know it somehow. Okay. Take signal. What's wrong with you? This way I can get it. Oh, yeah. This looks better. Looks better. 3, 3, 5. 4, 4, 0 must be another one. Oh, yeah. Here is a pair. 1 megahertz, 105, and should be the somewhere. There should be the way, I can show it. I can show the whole picture from the blue line. It's a sum of them all. Take a look. This one, 1 megahertz. It's a signal from generator. Heterodyne, 1.42. The difference. Here is the difference. 0.44 megahertz. And here, the sum 2.44. And this one, 2.88, is plus second harmonic. So, see, 1, 2, 3, 4, 5, there will be more signal. If I apply a bandpass filter, look what will happen. I'm applying this and this. From the whole spectrum, only one line remains. This one. This is line shows 440. I cut all except the difference. And now and now what you see? What's this red line? .444 central frequency plus 445. Oh yeah, 447, and this time 449. What happened? With this trick, sum them all and filter the difference. I got my signal. I got the signal spectrum after modulated, but on which frequency? On the difference between signal and heterodyne. Now I have my signal F444 plus 1 plus 3 plus 5 minus 1 minus 3 minus 5. I got my signal spectrum. Oh no, I got my camera damaged. Here it is. I got my signal spectrum transferred to interim frequency. It's a trick commonly used in communication. See what the problem is? When you need receiver for only one frequency, it's easy. But when you need receiver what can be tuned to different frequencies, you will need a bandpass filter with very narrow characteristic and adjustable. It isn't easy. It's very hard to create things. So idea of so-called super heterodyne receiver dominated communication market for many, many years. Here is your array of signal or something like this. You may have gain at high frequency. For good receivers, you will get. For cheap, not. And next, frequency conversion stage. Frequency to frequency. Powered by local source, local heterodyne. High frequency amplifier, maybe for good receiver, it will be selected. So it will preliminarily select some band from the area of signal. With this thing, you will get output at interim frequency. Now, you need to design a good bandpass filter and perform your signal processing. But anything you receive, you will get on one constant frequency. So your filter your selected filter, you may have Clark's filter. If you need a very narrow band, for example, you receive a telegraph. This monster has also a Clark's, but it's very narrow frequency. So you have a filter on the interim frequency. It may be adjustable. But 1 second, I'll show you a masterpiece of design. If I can leave, absolutely no guarantee. I'll try, but this is 1/3. The thing I'm carrying is 1/3 of the real first-class receiver. Its upper part, lower, approximately this size. Here, how to show it? This one had a double frequency converter. Not once, but double. These are coils of interim frequency filter. These all are coils. 2, 4, 6, 8. And on the other side are capacitors. This symphony of capacitors used to create variable bandpass. This thing can have bandpass from 1 kHz to 80. Set of interconnect. They have it's a set of coupling network coupled with variable capacitors. This array creates a variable bandpass. That's what mean class 1. It's only 1/3. Real receiver. And this part to receive single sideband, it's a BFO also. No one makes things like this today. This one, no, I don't have a serial. It's a series 6, but it should be somewhere around 1957, 58. One second. It should be. It's somewhere. 1961. This is technology. This pure, it's from 70s. I think it's 1972 or 73, something like this. Here we have one coil heterodyne, one coil input amplifier, one for signal. One variable condenser with 2 sections. One changes heterodyne frequency, one selective. And all these nice white coils are this part, where 4 are in a row. They are connected in series. It's an interim frequency filter. Then detection, amplification, and it's a radio. When it's manufactured, I don't see. I don't see. Indeed. Oh. 79. But the design approximately, I saw a sample 1976. So it's from 70s. Pure. Today usually they can be a frequent conversion and then direct digital processing. Because air become noise. This thing do not convert frequency because in that time only one broadcaster only stayed. Then time changed. By the way, interim frequencies you can name manufacture state by interim frequency. Civilian receivers Soviet Russian will have 465, German 472, United States 455 for AM, and 6.5 or 10 for FM, but we will speak for FM later. This, what's good in heterodyne? Spectrum remains unchanged. With the same trick, for example, power line carrier. You would like to transfer something using power infrastructure. What will you do? You will transfer your data to the, let's say, 100 kilohertz frequency, and then transmit it, and everything will go smoothly. Or not. Spectrum transfer with heterodyne. Oops, nothing happens. Super heterodyne. Maybe you'll be able to get something from this. But here is my original signal spectrum. Heterodyne. I'll show this tomorrow once more. And salvage teaching aid can sleep for a year. No, not for a year. I'm wrong. I'm showing this 3 times a year. 2 times in Latvian and 1 in English. I'm the last one who has this say. All other scrap. Oh. How to focus. So, conclusion. By mixing with special mixer your signal spectrum with local generator called heterodyne, and then applying bandpass filter on a frequency of difference, you can transfer your signal spectrum to the different frequency. And this, what this gives you? Ability to create main, the most signal processing path for one particular frequency. Only input stage and converter are frequency variable. The whole most of your system will be frequency independent. There is one moment for receivers built on this schematic. There is one how to say, underwater stone. The problem what there is so-called mirror channel. On the, I had 1 megahertz, 144, interim 44. But there is also mirror channel 188, which will also come with lesser amplitude. That's why really high-end receivers do have double frequency converter to cut off conversion, to cut off this mirror channel. And super high-end receivers, top, triple. Like monsters occupying the whole room. No. Relatively small models also exist, but super long range or military intelligence receivers are built with triple conversion and triple set of selective networks and extremely carefully created heterodyne, because frequency stability is dependent on stability of first dyne. They have extremely well made heterodyne networks. Thermal answer life is constant temperature, hermetically sealed, and so on and so on and so on. Masterpiece of design. And price tag, like my year salary. Okay, I don't see many viewers. I don't see many viewers, that's mean. What I can